Assalamu alaikum. Dear learners, I hope you are fine and have watched my previous videos in which we talked about robot dynamics and PID control of robotic manipulators. This video will discuss and implement another controller which is much more straightforward and logical than PID controller. Yes, I'm talking about computer torque controller. So let us first review a bit of basics to grasp what we are going to learn today, and then we will move on to MATLAB for implementation of computer torque control on our 3 degree of freedom non-planar manipulator. Just to recap a bit, this was a general control loop diagram that we considered, and I said that feed-forward compensator is necessary for predicting the disturbance arising because of the movement of other links. Prediction of this disturbance is necessary because we are controlling an individual joint only, and it would be impossible for a simple PID or PD controller to reject the disturbance on its own, especially when the disturbance is time varying, that is configuration dependent. In the previous video on PID control of robotic manipulator, we kept the feed-forward compensation quite simple. It was just a proportional feed-forward compensator that was just amplifying the input signal. The drawback of this was that the PID or PD controller must work a lot. We had to carefully tune the parameters through an optimization routine, and then the controller was able to move the robot to a desired set point. Furthermore, as per my suggestion, if you have tried to use the same PID tuned controller with a varying trajectory, then you must have seen that the controller was unable to follow the trajectory perfectly. I'll reiterate this point when we get to the simulation part later in this video. So what should be the remedy for these problems? That is, how we can track the varying trajectories efficiently. Well, believe me, a simple PD controller is all we need for that. But the prediction of disturbance has to be much more efficient. This is what a computer torque controller does. We are going to use the same block diagram, but this time the feed-forward compensator will not be a simple proportional compensator, but it will utilize the robot dynamics equation and approximate the torque required for compensating the disturbance. Remember that the torque generated by the inverse dynamics of the robot was not suitable for driving the physical robot, but that torque can prove to be a much better approximation of the disturbance. The discrepancy in the required torque and the torque generated by the inverse dynamics will be handled by a simple PD controller. Though the shown block diagram explains the general working of the computer torque controller, but for implementation we must modify it a bit. This is what we are going to implement. Remember that the inverse dynamics was producing and summing up 3 different torques. Out of those 3 torques, torque required for overcoming gravitational forces and torque required for overcoming Coriolis and centrifugal effects may be lumped into one unit, whereas torque required for producing the motion can be treated separately. This is what's happening over here. The final torque being supplied to the robot is a sum of torques required for producing the motion and the torques required for handling the Coriolis, centrifugal, and gravitational effects. Modeling errors are now going to act as disturbances, but those errors are much smaller than predicting the feed-forward torque through a simple amplification. Now, as far as the motion of the robot is concerned, then a simple PD controller would be enough to handle that. Therefore, net acceleration when multiplied with the mass matrix of the robot will give us the torque required for the motion of the robot. The net acceleration is nothing but a combination of the desired acceleration and the acceleration produced by a simple PD controller by taking in the error in position and velocity. It can be easily shown mathematically that this error is bound to go to zero no matter what values of proportional and derivative gains are used. Therefore, we don't need any tuning. You can choose any value of Kp and Kd. These values are going to affect the speed and overshoot of the response only. So, no matter what values you choose, the robot will start following the trajectory sooner or later. So, dear learners, technically we have linearized our nonlinear robot by introducing inverse of our system in the feed-forward path and then used a simple linear controller to control the behavior of our robot. I hope you have grasped the general concept of the computer torque controller, and now let us move to MATLAB Simulink environment for implementation of this control scheme. So this is the Simulink environment, but before going on to implementing the computer torque controller over here, let me recap that what we did last time and what we got and why we need to move towards computer torque controller. So these are the PID controllers that we tuned in the last video, and these were perfectly tracking the reference set points that we were giving to them. Over here, if I open the signal builder, you can see that these are the 3 signals that I am providing as joint angles. And let me run this thing to see that how the robot was following these 3 set points. So here is the simulation, and you can see that the manipulator is following the angles which we have provided. Just to be sure, let us watch the scope and see that what's happening over there. So here is the scope data, and you can see that all three reference set points are being followed perfectly. This yellow line is the first joint angle, whereas I'm closing the other reference lines so that you can see better. So over here, the yellow line is the first set point, that is the set point for joint number 1, and green is the measured angle which the robot traverses. You can see that after a particular time, it follows that set point perfectly. And same is for this second set point. This blue one is for the second joint, and this purple line is the measured second joint angle. And same goes for the third joint. That is, this red line is the third joint reference point, and this cyan line is what the robot did. So till this point, everything is fine. Now let me give this PID controller a varying trajectory, and let's see that whether this PID controller is able to make the robot move on that varying trajectory or not. So for that, I have to modify this input trajectory, and I have already done that, so I'm just going to place the things over here. So now I have attached this trapezoidal velocity profile trajectory block over here, which is generating a varying trajectory, and all of the rest of the things are the same. I am using the same PID controllers with the same tuning parameters. So let me run it and let's see what happens now. So here is the simulation, and by simulation it seems that PID controller is doing a great job. But let us move to the scope and see that what trajectories we provided and on what trajectory the robot is moving. So in this scope, once again, this yellow line, which I've turned on right now, is the trajectory that we are providing to joint number 1. And this green line is the trajectory on which joint number 1 is moving. You can see that how much different is that. This is because of the fact that PID controller need sometimes to achieve the set point. But before that set point is achieved, the set point has already changed. So the error is always changing. And same goes for the other joints as well. So now this blue line is representing the joint angle which we are providing to joint number 2. And this magenta or purple line is the angle which the robot's second joint is moving through. So you can see the discrepancy over here as well. And just let me turn off these things so that you can clearly see the third joint. So this is the joint angle which we are providing to the third joint, and this cyan line is the joint angle through which the third joint is moving. So you can see that PID controller, although was very good for the set point tracking, but it is not able to track the reference varying trajectory perfectly. So this is the reason that we have to move towards some other type of controller. So I'm going to provide the same trajectory to the computed torque controller, and we will see that it will be able to track this trajectory perfectly. So now let's move on to the implementation of computed torque controller, and then we will provide the same trajectory to that controller as well. So here I'm going to implement a computed torque controller. I have placed few things already. Over here I have used a trapezoidal velocity profile generator block, and I'm providing the same trajectory that I just provided to the PID controller. And on this side I have my same 3 degree of freedom non-planar articulated robot, and I am measuring its angles, 3 angles, and comparing those 3 angles with the reference angles which I am providing. And these two things are going into this box and then into the scope, so that I can see that what reference trajectory I am providing and on what trajectory my robot is moving. So we need some kind of controller in between over here that can provide torque to this robot, and it can move on the desired trajectory. So to implement the computed torque controller, we need to implement a mathematical equation that I showed you in the opening minutes of this video. Let me just write that equation over here for your reference. So that equation was something like that. We need a torque, and that torque was sum of 3 different torques. The first one was mass multiplied with required acceleration, that is q double dot, plus kd into error derivative, or I can say that it is desired velocity minus measured velocity. So I am writing qd, which is the desired velocity, and qgm, that is the measured velocity. And after that I have to add kp multiplied with error, that is desired angle minus measured angle. So this is what is going to be multiplied with mass matrix, and this will be the first portion of the torque that we need. The second portion would be the torque required to overcome the Coriolis effects, and the third portion would be the torque required to overcome the gravitational effects. And for these two torques, I'm going to lump them up in a single variable and write n over here. So we need to implement this equation. And for implementing this equation, we require these things. We require the mass matrix, we require the desired acceleration, we require the desired velocity, then the measured velocity, desired angle, measured angle, and the torques required to overcome the Coriolis and gravitational forces. So the three things that are particular to the robot's dynamic structure, they will come from the robotic system toolbox. And those three things are this mass matrix, the velocity matrix, and the gravitational forces matrix. So these three things are going to come from the robotic system toolbox, whereas the other things that are the required acceleration, the required velocity, the required angle, these three things will be coming from this trajectory generator, and the measured velocity and measured angle, these things will be coming from the robot from this side. So I guess we have all the things that we require, and now we should start implementing this equation. So the very first thing that I need is I need a mass matrix. So I'm going to write a mass matrix over here. So this is joint space mass matrix, and this joint space mass matrix will be calculated by using the configuration of the robot. And the configuration of the robot is coming from this side over here. Just remember that configuration is nothing but an array containing all the joint angles. So these things are coming from over here. And this block is going to provide me the mass matrix. So to use this block, I need to tell this block what rigid body tree it should use. I've already loaded the rigid body tree of my robot over here, so I'm just going to select that, and that's it. Now the second thing I need is I need a velocity product that will give me the torque required to overcome the Coriolis and centrifugal forces. So this block requires the configuration and the joint velocity as well, and it will give me the joint torque needed to overcome the Coriolis forces. So I have the configuration over here, and I have the joint velocities over here as well. So I have both of these things. I can provide these things over here, and once again I have to tell that what rigid body tree it should use, and once again I'm going to use the same rigid body tree over here. And the last thing we need is we need a gravitational torque matrix, and I can get that block from robotic system toolbox. Once again, it requires only the configuration. So once again, configuration will come from here, and it will give me the gravitational torque, and I need to tell it that what rigid body tree it should use. So that's it. Now I have the three torques coming from the dynamic structure of the robot. So according to this equation, what I need to do is I need to multiply this mass matrix with this thing, and then I need to add the velocities and the gravitational torques into this sum. So to keep the things simple, let me close these things into one system and work over there. So I've created a subsystem, and this subsystem will be my computer torque controller. Let me rename it as computer torque controller. So inside this block, we are going to do everything. So first, let me delete these extra nodes, because the configuration is coming from here, so I can attach all these things over here. So the first input this block needs is the configuration. The second one is the joint velocity. I need a third input, which would be the desired joint angle. So I'm going to label it as desired joint angle, which would be Q. Then I need QD over here as well, that is the joint velocity, and then QDD as well, that would be the joint acceleration. So these three ports are going to act as the input ports, and the output of this system would be nothing but a simple torque. So I'm going to adjust the output in a bit. So this configuration and this desired angle, they are going to be subtracted to generate the error. So I need a subtractor block. So, and for that I'm going to use an add block, and in the add block, the first symbol would be minus and the second one would be plus. And over here I'm going to attach the configuration, that is the measured angle, and over here I'm going to attach the desired angle. So desired angle minus the measured angle is going to give me the error over here. So this error would be multiplied with Kp. So I need a gain, This gain would be called Kp, and I'm going to do the same thing with the velocity as well. And over here, this thing would be called now Kd. So I'm using the velocity and using the desired velocity over here. This would be the error in velocity multiplied with Kd. And now I have to add these three things up. Now remember that I needed the desired acceleration, which is coming from here, the desired velocity error multiplied with Kd, which is coming from here, desired joint angle error multiplied with Kp, which is coming from here, and I need to add them. So once again, I need an adder, but this time I need three additions. I'm going to add these three things up like this. And now this thing is going to be multiplied with the mass matrix to give me the first torque required for the movement of the robot. So over here, I don't need this thing. I'm going to delete it. And I need a product block so that I can multiply the mass matrix with this thing. And inside this product block, I need to select matrix multiplication. So on top, I'm giving the mass matrix, and from the bottom, I'm giving these three things. So now over here, I'm getting the torques required to generate the motion in the robot. And now I need to add the torques required to overcome the Coriolis effects and the torques required to overcome the gravitational effects. So these two torques are over here. So I'm going to use this thing. And once again, I'll be using an adder block to add these three things up. So I have used the adder block to add these three things up. And this would be the output. And I'm going to call this thing the output torque. Sorry. So that's pretty much everything. We have implemented the equation, which I showed you over here. Let me take it inside. So this is the equation that we implemented. We multiplied the mass matrix with this thing and then added this variable n, and this n is nothing but a combination of these two torques. So this is the desired torque that which we are going to feed to our robot. Now the only thing that remains is that what should be the values of Kp and Kd. Well, believe me, you can choose any values. For all the values, ultimately the robot is going to follow the trajectory. But the larger values you're going to choose, the quicker the robot is going to move towards the desired trajectory. But the larger torques will be generated. So it depends on what kind of torques you require, what kind of torques your hardware has. So you cannot generate torques more than that. So you have to limit the values of Kp and Kd. So right now, if I'll use, let's suppose for Kp, I use 10, and for Kd, I'm going to use, let's suppose 2. So let's see what happens. So on the outside, I'm just going to connect this torque to this robot. And on the inside, I need to provide these things. I need to provide the Q, which is the desired angle. I need to provide Qd, which is the desired velocity. Q double dot, which is desired acceleration. Joint velocity will be coming from here, and configuration will be coming from this one. So I've just placed the things a bit tidily, and now let us run it and see what happens. So here is the simulation, and in the simulation it seems that the robot is moving on the trajectory that we provided, but we have to move towards the scope to see what really is happening. So inside the scope, you can see that the rating trajectory is being followed much more better than that was being followed by the PID controller. If we just look on the first joint, which is this one, then the first joint is being followed quite perfectly. And for the second joint, it is once again being followed nicely. But the third joint, there is some error in that, a visible error in that. We can easily remove this error by just increasing the Kp and Kd value, because right now this computer torque controller is a bit slow controller. So we need to increase its speed by just increasing the Kp and a little bit of Kd as well. So let me go over here and increase these values to, let's suppose, 100. I'm using 100 for Kp, and for Kd I'm going to use 20. Now once again let me run it and now see that what happens. So here is my son. He is a naughty boy and he is disturbing me while making the video. So right now the simulation is running, so I'm waiting and he is disturbing me. So once again, this is the simulation and we can see that the robot is moving fine over here. But to be sure, we have to go to the scope and see what is happening over there. So now you can see that these are the three trajectories of the joint angles. And if I just close the other two, just to focus on the one, now this is the trajectory. The yellow line, which is not visible because it is exactly beneath the green line. The yellow line is the reference trajectory and the green line is the follow trajectory. Whereas this blue line is the reference trajectory for joint number 2 and this purple line is the follow trajectory for joint number 2. You can see that the robot is exactly following the trajectory, and this one is the reference trajectory for the third joint that was not being followed quite perfectly last time, but this time, and this cyan is the trajectory of the third joint that is being measured. So now you can see that the third joint is also moving quite perfectly. If you increase the Kp and Kd more, the torque output is going to increase and these trajectories will be followed much more strictly. If your robot requires to move at higher speed and require to operate with high accelerations and decelerations, then the values of Kp and Kds has to be much larger. So dear learners, I hope you have understood that what computer torque controller is, and now you can easily implement this controller on your MATLABs and you can simulate your robot. Keep one thing in mind, that computer torque controller is going to require significant amount of computing power. So the simulation is going to take some time. I have cut that portion where I was waiting for the simulation to be completed. Just to give you an idea, to complete the simulation of these 3 seconds which I have provided over here, my PC took around 1 minute. So keep in mind that it is going to take time and be patient. So that's everything for this video. If you have any queries and you didn't get anything, just rewind and see that part again. And if you still have any questions, then I'm always available through YouTube channel comments. Thank you and take care.